Hi everyone, my name is Elizabeth Chen.
Negro. I'm Jack Lorenz.
And today we are going to be talking about our journey of structural refinement of three binary alloys.
Okay, so first we'll be going over what is neutron diffraction. So neutron diffraction is a technique used to determine the atomic arrangement of crystalline materials. So in this figure, we have figure 1, where a beam of neutrons is directed at a crystal sample. And in figure 2, the crystal sample scatters the neutrons because of the atoms inside into different angles, which creates a diffraction pattern. And then in figure 3, we have a detector that basically measures these scattered neutrons and determines the different angles, which creates a diffraction pattern. And so scientists can use this diffraction pattern to kind of act as a fingerprint for the crystal structures. So now that we know how these angles determine, this is where Bragg's law comes in. So basically, once the neutrons scatter from different planes within the crystal, scattering waves can reinforce each other, and a diffraction peak is produced. So this only occurs when Bragg's law is satisfied, and Bragg's law is the equation that I have up there. So d is the spacing between crystal planes, lambda is the neutron wavelength, and beta is the diffraction angle. And so by measuring these diffraction angles, we can determine the spacing between planes and ultimately the crystal structure. So now that we know how diffraction works, why do we use neutrons instead of X-rays? So neutron diffraction provides structural information that X-ray diffraction cannot always obtain. So for example, neutrons interact with atomic nuclei rather than electron clouds. And because of this, it makes them better at detecting light elements such as hydrogen and distinguishing more similar elements, and since it's more sensitive to magnetic boring. So by combining neutron and X-ray diffraction, scientists can use these two techniques to provide a more complete picture of material structure. So finally, what does a diffraction pattern show? So a diffraction pattern is made up of a series of peaks, and there's three main factors that we can read from these peaks. Number one being the peak position, which tells us the spacing between crystal planes through Bragg's law. Number two is peak intensity, which can provide information about the arrangement and types of atoms in the crystal. And then finally, the peak width, which can indicate the crystal quality. So the more narrow the peak, the more well-ordered the crystal is, and the more broad, it means that it's smaller crystallized, it could be strained or defects. And so together we can use these features to allow us to determine the crystal structure and evaluate the quality of these samples.
So this is the instrument that we use to measure our data, which is called ARCS, or the Wide Angular Range Chopper Spectrometer, at the Oak Ridge National Lab. And so how do you use this instrument? Well, first you load the sample into the sample stick, and then you lower it into the instrument below where it's measured, and neutrons are fired at the sample. And so by tracking how those neutrons bounce off and change energy, the instrument records how the atoms inside the sample are vibrating. And so for each alloy pair, and our mentor made phase diagrams. And phase diagram shows for any given mixture of two elements what temperature it melts at and what state it's in. And Anne chose the composition marked by the orange line here, which is known as the eutectic. And the eutectic is the mixture with the lowest possible melting point for that pair of elements. And unlike most compositions, it melts at one single sharp temperature rather than over a range. And so this made it a consistent, well-defined point for us to compare across our three alloys. And the composition for each is lead with 75% tin, bismuth with 61% tin, and tin with 15% zinc. And so this is how our raw data looked like out of the ARCS instrument. And so here is the elastic line, which represents neutrons that bounced off the sample without gaining or losing energy. And this means that they didn't interact with atomic vibrations at all. And so Anne took this data and sliced it right down the center and gave this data to us, which looks kind of like diffraction data. And so we took that data and put it into GSAS2, which is the software that we use to analyze.
As a group, our research was driven by the fundamental curiosity about the atomic scale mechanics of phase transitions. Specifically, we wanted to answer the question, how do atoms jiggle? On top of this, we also wanted to look at the velocity at which these atoms jiggle. We know that as materials reach higher temperatures, these vibrations or jiggles increase in speed and amplitude. This led to our next major question: how do these vibrations or jiggles contribute to the latent heat, as well as how much energy is required to melt the material? We know that the latent heat represents the energy threshold needed to break the bonds of a solid lattice, and we suspected that the vibrational energy of these atoms was the key to figuring out this connection. This formed the basis of our group's central hypothesis. We believe that finding the structure of these materials will help characterize the samples and make conclusions about melting entropy and latent heat more apparent. Our logic was that if we could precisely map the crystal structures of our three binary systems, the bismuth tin, lead tin, and zinc tin alloys, and compare them to their pure components, we could see exactly how the atomic environment dictates these thermal properties. Ultimately, our focus was to prove that the structural arrangement of the atoms is what determines the energy and disorder involved in the melting process.
So now we'll be talking about what we did over the Caltech SRC program. So first we studied three binary alloys, which were zinc tin, lead tin, and bismuth tin. But all the sample preparation and the initial data collection were all handled by the Red Fultz lab. And so next we took the data that Anne gave us and built a two-phase red field refinement in GSAS2, the software that we use. And we manually refined each parameter in each window. And so what we did was we started to refine the background first, because we found that if we refine the background plus the scale factor simultaneously, this causes instability with the graph. So we first refined the background, followed by the scale factors, and then the structural parameters. But our starting instrument parameters, things like peak width and shape, were provided by our mentor, Anne. And for me, I personally got tired of doing step 2 and step 3 over and over again, going through each window and playing with the numbers to change like the parameters. And so I created an automation using Python to help speed up the process and also track better like the different options that are better to make the calculated run.
Alright, so I'll be going over the crystal structure that I covered, which was lead tin. So lead being a cubic structure, and then tin being a tetragonal structure. And so here's my fitted data that I created. So the fraction patterns nodes here is peak. Okay, so basically what I have here are the blue crosses are the experimental neutron diffraction data. The green line is pattern calculated by GSAT2, and then the red line models the background signal. The blue tick marks indicate expected Bragg reflection points, and the bottom residual plot shows the difference between the observed and calculated patterns. So for my results, the calculated model reproduced the major diffraction peaks, indicating a reasonable structure fit. Some peaks, particularly the strongest peak around 13 degrees data, do not perfectly match the experimental intensity. So the residual plot also shows subregions around it can be improved. And so in the future, possible improvements for my data could be to refine the background and scale factor, adjust lattice parameters and peak profile parameters, and as well as refining the atomic displacement and parameters and occupancies. But this is an iterative process, so you can always have a better fit and create better accuracies within the team.
Here's what the refinement revealed after fitting our two-phase model to the bismuth tin diffraction pattern, with bismuth being a trigonal shape and tin being the tetragonal shape structure. This model successfully confirmed that the presence of both hexagonal bismuth and tetragonal tin. As you can see across the plot, the calculated green curve generally follows the blue observed data peaks, and reflection ticks align with the majority of the peaks. To ensure proper phase stability, I had temporarily held the phase fraction constant while refining bismuth's A and C unit cell dimensions to align its reflection ticks directly with the raw data peaks. This targeted step securely anchored the bismuth phase, allowing the scale factors to refine cleanly. This resulted in a stabilized model with a final reduced chi-square score of 3.454. This confirms that we have correct structural phases, but also that the score reflects what we haven't fully resolved. Specifically, at our strongest low angle reflections around 10.5, 14, and 21 degrees to theta, our model overpredicts peak heights, resulting in the sharp downward spikes in the residual plot below. This mismatch indicates preferred orientation, where the metallic bismuth grains align along specific directions rather than acting as completely random powder. So, while we successfully established the fundamental crystal structures, fully modeling sample texture and peak intensities remain a limitation as we move on to comparison.
So this is how my crystal structures look like for my alloy. And so for zinc, we have a hexagonal crystal structure, and for tin, we also have a tetragonal structure. And so now going on to my graph, we can see that overall, the calculated line tracks the observed data pretty well. And so this tells me that the phase and the basic structure are correctly identified. But we can see that the clearest issue here is around the two peaks of 12.5 degrees and 18 degrees to theta. And so the calculated line intensity falls noticeably short of the observed data. It shows up as sharp peaks in the residual plot below, which is the black line. And also my weighted residual, or the RW or the RWP, measures how closely my calculated pattern matches the observed data. And so the lower the value of the RW, the better it is. And so what I got for my weighted residual was 31.735%, which is on the higher side for this type of refinement. And so there are two reasons for this being that high. The first reason is that I only refined the instrument parameters. And so I refined the background, which is the red line, and then also like the peak shape. But I haven't adjusted the structural parameters like the unit cell or sample parameters. So this graph hasn't been to like the fullest potential yet. And so second, the other reason is that the pattern we just saw at those two strongest peaks is consistent with preferred orientation. And so what this means is that the tiny crystal pieces in our sample might not all be facing in random directions. So some directions might show up more than others.
Alright, so just a quick recap, we successfully refined the crystal structures of three binary oscillator systems, which were lead tin, bismuth, and zinc tin, and then we used the neutron diffraction data together with GSATs to compare the experimental data with our calculated structural models. And so basically what we learned is that structural refinement is an iterative process that requires repeated adjustments to improve the fit. GSATs 2 provides a large number of refinement parameters, including background, scale factor, blast parameters, peak profile, atomic positions, thermal displacement parameters, and atomic occupancies. And so many of these parameters are interconnected. So changing one can influence several others, but we need to keep on changing multiple of them so that we have a better fit. So up here I used Elizabeth's data as an example. She started off with some pretty not accurate fit data, but then through an iterative process was able to get a lot more accurate to the experimental data. So some key takeaways for that: refinement requires both computational tools, but also a sort of scientific judgment to figure out what to change, and it's not completely an automatic process. Multiple refinement cycles are often needed to achieve a model that accurately represents the experimental data. And even when a reasonable fit is obtained, there is often room for further improvement. And so this is important because accurate structural models are essential for understanding and the properties of materials. And then these refined structures can provide foundations for future studies of atomic vibrations, melting entropy, and isotopy environment algorithms.
Although manually performing the refinements improved our understanding of the GSATS2 workflow, it also exposed several inefficiencies. Refinement required repeatedly selecting parameters, running the fit, evaluating the results, and making repeatedly selecting parameters, and making additional adjustments for each of the three alloy systems. As the number of trials increased, tracking which parameter combinations had already been explored became increasingly difficult, making the process both time-intensive and prone to overlooking potential potentially better solutions. To address these limitations, Elizabeth has begun on a Python-based automation tool that uses GSUS2 scripting interface. Rather than relying on manual trial and error, the program is designed to systematically test refinement parameters and identify more effective combinations with greater efficiency. Future works will focus on completing the automation, applying it to finish the remaining unit cell refinement, and expanding the workflow to all three alloy systems. As a result, if we were able to fully automate our approach, it would improve consistency, reduce refinement time, and provide a stronger basis for comparing results across different samples.
We want to give a huge thank you to first the Caltech SRC program for giving us this opportunity, and Professor Fultz for sponsoring this, us. And then we also want to give a huge thank you to Kyle and Andrew for helping us through this process, even though they weren't our mentors in this program. And finally, we want to give a huge thank you to Anne, our mentor, who helped us along every step of the way. Thank you so much, Anne, for all the opportunities that you have provided us and all the information that along the way. And please give a huge round of applause for the Brent Fultz team that is here to cheer us on today. Thank you. Are there any questions? Yes.
How many free parameters are in the model that you're fitting to this spectrum?
So we have sample parameters, unit cell, and like we also have in the phases themselves parameters that we can adjust. To be honest, we didn't count how many there are, but there are quite a lot in GSAS that we have to change.
Is it like tens or thousands or millions? Yeah.
I mean, within each window, there's quite a few, like about 5 or more than that. Yeah. Yes, Andrew?
So some of the peaks in our object, do you think it could be from interactions between the two element types?
I think that it could be a variety of things. Most of what we were discovering is that it was in fact some of the phases were not captured because there are multiple phases that you can find for each element. But it could have also been like other things that we're testing with. One of the things that I found was that sometimes my instrument parameters were inaccurate, so I had to adjust those. And after adjusting them, the peaks were further corrected, more accurate.
Temperature would be set. Above the setting.
Yeah, I'm pretty sure the data that was given to us was just at room temperature. Yeah.
Yes.
Some of your bits that receive the background, did you make sure just to cut those end bits of the data off because the background can be a bit referring to some serious.
Yes, we did not cut off the peak for the background because we thought like there are data there that we do need to calculate. But if that's probably the case of where it's gone wonky, then probably we should have cut it. Yes. Are there any other questions?